Hello everyone, I am Souradeep Chakraborty, a computer science PhD student at Stony Brook University. I am going to talk about our work on unsupervised and semi-supervised co-salient object detection via segmentation frequency statistics. A part of this work was done during an internship at Amazon. The goal of our work is to detect co-occurring salient objects in an image group when no label or very limited label is available for training. For example, here is how the commonly occurring teddy bear object is segmented for each of the three images in the group. A majority of the existing models for CoSOD are fully supervised, that is, they use segmentation annotations as labels for training their models. This annotation requirement is a drawback for these models. In this work, we solve CoSOD when no labeled data or significantly less labeled data in terms of segmentation annotations is available for training. There are two main drawbacks of existing models which we address in our work. For the existing fully supervised models, collecting segmentation annotations for supervised co-salient object detection is expensive. And the prediction performance of the existing unsupervised as well as semi-supervised models is significantly worse compared to the existing fully supervised models because they fail to make efficient and effective use of the vastly available unlabeled data. Our work derives motivation from several real-world applications such as e-commerce, content-based image retrieval, satellite imaging, biomedical imaging, etc. We have three main contributions. First, we propose a simple yet effective unsupervised approach for CoSOD that leverages self-supervised single-image semantic segmentations and self-attention maps to generate pseudo-labels for training. Second, we show that CoSOD can be significantly improved using large unlabeled datasets, example ImageNet 1K. Finally, we propose a novel approach for semi-supervised CoSOD that effectively propagates knowledge from a limited label set to a much larger unlabeled set via confidence estimation and cross-region correspondences between the labeled and the unlabeled sets. Now let me introduce you to our unsupervised model US-CoSOD. Given a group of images containing a common salient object, in this case a butterfly, we first obtained single image segmentation mask from STEGO, a self-supervised semantic segmentation model, and self-supervised self-attention maps from Dino, a popular self-supervised feature learning model. We considered the average attention map across all attention heads from Dino as the foreground object segmentation because this has been shown to highlight salient foreground regions. Next, we compute the co-occurrence frequency of the discovered categories across all images in the group. For each image, we next compute the top k frequent STEGO categories and finally select a single unlabeled category based on the intersection score between the STEGO and the Dino masks. Specifically, we consider the most frequent STEGO mask that has the highest saliency value as the zero ground truth mask. For example, in the instance depicted, mask ID 2 gets selected over mask ID 1 as mask ID 2 has a higher saliency value compared to mask ID 1. This filtering step ensures that the selected segmentation corresponds to the most common yet salient object, therefore preventing co-occurring backgrounds from being considered as the pseudo masks. Next, we train an existing fully supervised CoSOD model, DCFM, using the pseudo ground truth mask as labels that are obtained in the previous step. During inference, we simply pass the images in the test image group through the trained model to obtain the final predictions. Note here that our model only uses the self-supervised component models such as STEGO and Dino during training to generate the pseudo labels, but not during inference. Now I shall introduce you to our semi-supervised model SS-CoSOD. Given a small set of labeled images and a much larger set of unlabeled images, we follow a two-stage approach for producing CoSOD predictions in a semi-supervised manner. The first stage involves pre-training on the label set. The next stage involves semi-supervised training using a student-teacher approach. I will explain these two stages in details next. We first pass the images in the label set through DCFM, an existing supervised CoSOD model. We initialize the weights of this model using that of our US-CoSOD model. This initialization provides better performance compared to initializing from a pre-trained VGG16 model which has been trained using ImageNet. This network is trained via the IOU loss between the predicted and the ground truth segmentations, as well as the self-contrastive loss LSC here from DCFM. Here, we also train a confidence estimation network in order to estimate the reliability score of the model prediction. For training, we use the labeled image set as the input and the corresponding segmentation F measure scores of the pre-trained model FPT predictions as the ground truth. The model is trained by fine-tuning a ResNet 50 backbone trained using the Dino method, using the mean square error loss on the F measure scores. In the second stage, we employ a typical self-training framework with two models of the same architecture, namely the student and the teacher networks that are initialized from stage 1. The student model's weights are updated via backpropagation, while the teacher model weights are updated using exponential moving average. By jointly passing both the labeled and the unlabeled sets to the student network, we leverage the benefit of learning cross-pixel similarities across all images in the group to effectively propagate object co-salience information from the labeled set to the unlabeled set. The unsupervised loss between the student and the teacher prediction is weighted using the confidence score predicted by the CEN module G for each unlabeled image. We combine the supervised loss computed from the label set from stage 1 and the unsupervised loss for the unlabeled samples from the second stage to constitute the final loss. For training, we use the COCO 9213 dataset and additionally constructed a dataset of 150K unlabeled images by selecting 150 images per class from the training subset of ImageNet 1K to train our models. We used three popular CoSOD benchmark datasets, COCA, CoSAL 2015, and CoSOD 3K for evaluating the performance of our models. Here, we compare the predictive performance of different unsupervised CoSOD baselines with our model. We see that our US-CoSOD model produces the most accurate segmentations. Here, we qualitatively compare the CoSOD predictions from different baselines with our SS-CoSOD model. We see that our US-CoSOD generates reasonable prediction masks, and our SS-CoSOD approaches further improve these predictions while performing better than the fully supervised DCFM trained with limited labels. More examples next. Here we show that while multiple categories can coexist in an image group, example flowers and butterflies, our Dino plus Stego model extracts the more co-salient butterflies, guided by our Dino self-attention maps. Also, our US-CoSOD model, trained using the pseudo-co-saliency mask, improves these predictions via improved structural consistency. Coming to quantitative evaluation, in this table, we compare different unsupervised baselines with our model. We see that our US-CoSOD model, trained on the 150K images from ImageNet, achieves the best performance. However, increasing the number of images to 450 per class slightly reduced the model accuracy. We attribute this to the fact that adding more unlabeled images to the training set may lead to erroneous training due to the noisy pseudo-ground truth masks generated by the Dino plus Stego model, using which our US-CoSOD model is trained. Here, we compare the performance of different versions of our SS-CoSOD models using different proportions of labeled data. We observe a consistent improvement in SS-CoSOD performance when the reliability scores from the CEN module are used to modulate the unsupervised loss. Joint unlabeled and labeled student training further leads to a small but consistent improvement. Here DJ indicates disjoint training. We further improve a significant improvement in performance when the ImageNet 1K dataset is used for semi-supervised learning. Here, we compare the performance of existing unsupervised and semi-supervised CoSOD models with our models. Both of our unsupervised and semi-supervised models outperform the corresponding segmentation model by a significant margin. For example, on the CoSAL 2015, our US-CoSOD has an 8.8% F measure gain over an unsupervised SOTA co-segmentation model, and our SS-CoSOD model has an 11.81% F measure gain over FASS, a semi-supervised CoSOD model. In conclusion, we presented a novel unsupervised CoSOD model based on the semantic segmentation frequency statistics, as well as a student-teacher-based semi-supervised approach with effective confidence estimation. Finally, we show that these models significantly improve prediction performance over corresponding existing models. Thank you.